Hello, and welcome to the Camtasia file with regards to object section properties. What we're trying to determine here is what is the cross-sectional properties of your object, not only in terms of area, your cross-sectional area, but its centroid, where the center of gravity is of the object, and how much resistance to bending does the object give you. For instance, we got an I-beam right here, a little plastic I-beam, a little rubberized I-beam. And as you can see, if I load it this way, with its section oriented in this direction, it's pretty strong. But if I flip it 90 degrees so it's oriented this way, it's actually pretty flexible. Same amount of force applied to the exact same object, but oriented two different ways, produces two different results in terms of its resistance to that force. The question is why? Let's take a look. Whenever you deal with residential building materials, you're familiar with a 2x4. In a house, you commonly will have a 2x8 or a 2x10 supporting up your basement. Why is it that we oriented our boards this way down in the basement instead of laying them flat this way? Well, they're both 2x8s, so they're both 2x8s, which means they have dimensions here of 1.5 inches by 7.25 inches. The actual dimensions, 1.5 inches by 7.25 inches. But why is it that we oriented our basement this way, up and down, versus laying them flat? We get a lot more headroom that way. Why is that? Well, let's take the first. What's the area? The area of a rectangle is equal to what? Base times height. In this case, what's my base? My base is 7.25 times my height, which is 1.5. Over here, I have an area total, which is base times height. My base, in this case, my base this way is 1.5. My height is 7.25. So I have case 1 over here. Let's delete this. And over here I'm going to have case 2, which is 1.5 for my base and 7.25 for my height. So we have case 1 and case 2. What's the area total? Area total is plus base times height. 10.875 for case 1, and we applied the same thing over here. Case 2 is 10.875. So they have the exact same area. The trick comes in to moment of resistance, or moment of inertia. I called moment of inertia. I commonly refer to this as units of bending resistance. We can derive how you obtain the moment of inertia, but realize that the moment of inertia is units of length to the fourth. It's a cross-sectional property, length to the fourth. It's kind of convoluted how you get there, so we're not going to bother how we derive the moment of inertia. We just know for a rectangle, I is equal to base times height cubed over 12. So my moment of inertia, or my units of bending resistance, I, for a rectangle, is equal to base times height cubed over 4. BH cubed over 12. So we know that for a rectangle. There's also I values in your book for circles, for triangles, for all your different geometrical shapes. You have this resistance to bending of each individual piece. For us, that we most commonly see, is a rectangle. Why? Because our boards are rectangles, our wood beams, they're rectangles. Our joists, engineered wood joists, I-shapes, 3 rectangles right here. We have channel sections for brackets, 2 rectangles. Everything can easily be broken up into rectangles for us in the profession. So we're going to stick with the basic concept of the rectangle is equal to base times height cubed over 12. So if we go back now and we figure out Ix is equal to base times height cubed divided by 12, I'm going to format this number to 1 decimal place. So for the first one, in terms of laying it flat like this, for that very first one, our resistance to bending, our units of bending resistance, we had 2. We had 2 units of bending resistance. So Ix equals 2.0 inches to the 4th. What about the other one? Look, when we flip that beam around, we increased from 2 to 47.6. So we went from 2.0 to an Ix of 47.6 inches to the 4th. We increased this over 23 times. We got 23 times more units of resistance to bending by orienting it up and down as we did laying it flat. And you can see that. When we take a flat beam and you start bouncing it back and forth, it's very flimsy when it's being carried this way. But when we carry it that way, it suddenly is very rigid to its own weight. Why? Weight acts perpendicular to the ground. So when we're carrying that 2x8 this way, it's flopping up and down. But when we carry it upright, and we carry it, it becomes suddenly very rigid, and this is the reason why. Do that geometrical change in the orientation. We haven't changed the cross-section at all, just how it's oriented. We increase 23 times more resistance to bending by going up and down versus laying it flat. And that's huge. That's immensely huge in terms of understanding why we need to know this. But we talked about how cross-sections aren't necessarily just beams. Let's do an I-beam. Let's take a look at this. I'm just going to make a big bulky one here. And let's give it some properties. Let's say this up here is 8 inches. This right here is 2 inches, and this isn't to scale. And TS, it's not drawn to scale. 10 inches, 2 inches, 2.5 inches, 3 inches, 2.5 inches. So this is our cross section. What can we do? We want to find out our geometrical properties of this. I can break this up into 3 pieces. I'll call this piece 1, piece 2, and piece 3. Now, for our 3 pieces, let's ID them first. I like to doing this because this is a clear documentation. Remember, the answer is only 10% of the solution. Clear documentation is 90% of your answer solution. The answer is only 10% is your answer. 90% is your documentation, which gives you 100% of the solution. If I can't duplicate your calculations, if I can't follow your progression of logic as somebody that's checking your work, I don't care if you have the right answer, that doesn't help us, because we need clear documentation on how you got that answer. So if we need it 6 months from now, 2 years from now, 5 years from now, if something's gone wrong and we're trying to figure out how you came up with this answer, if you don't have clear documentation on how you got that answer, it doesn't help us. Clear documentation is the key to understanding the progression of logic that arrived at the answer, so we can duplicate it. So, one of the things I like is this table layout, so I can clearly follow somebody's progression of logic. ID 1, 2, 3. Our geometrical shapes, base and height. What's the area base of problem 1? Well, 1 is going to be what? Base is 8 inches. The height is 2 inches. What about 2? The base is 3 inches. The height, 10 inches. What about section 3? We have 8 inches, 2 inches. So we can quickly figure our area of our individual shapes, which is going to be inches squared. So this would be 16, 30, 16 for a total area of 62 inches. So AT is equal to 62 inches squared. So that's our entire cross section, is this entire section right here. Is 62 square inches. Why is that important? Well, if we want to know the weight per foot of this section, that's vital. Let's say it's made out of concrete, right? This was a concrete beam. And we know that concrete weighs, Portland cement concrete weighs 150 pounds per cubic foot. So what is our weight per foot on this beam? Well, then our weight per foot of this beam is going to be 150 pounds per cubic foot times our cross section, area total, of 62 inches squared, right? And then we got to convert that. So we know we got 144 inches squared per square foot, which will allow the inches to cancel. The square feet will cancel with this to leave 1 foot. And what is that? So we have plus 150 times 62 divided by 144. So 64.6. So this beam right here, if it's made of concrete, would weigh 64.6 pounds per linear foot. That's how much this beam would weigh if it was made out of concrete. Would be 64.6 pounds per linear foot. That's why the area is important. Now we want to know how we want to determine the centroid. Where's the center of this object? Well, this one should be pretty easy because it's symmetrical. It's going to be in the middle. So I know the centroid is right here. But what if we don't know that? What if we have an irregular shape? Some shape that looks like this. Right? Some arbitrary shape. Let's extend this out a bit longer. Let's say like this. We need some point to start from, some central point. Let's assume we have a wall and a floor that's actually been plumbed correctly, so it's at 90 degrees. And let's bring that object down to our wall. First, I want to group this object. So the entire object will move. We'll set it on the floor, and we'll slide it over to the wall. So our 0, 0 coordinate would be right here. That's our 0, 0 coordinate. That's what we'll declare as 0, 0, the lower left-hand projection of this object, as if we fit it up against the wall. So that's where we want to declare 0, 0. That'll be our global 0, 0 point. For our case, where's our global 0, 0? Our global 0, 0 is going to be right here. 0, 0. We know the centroid of each of the individual pieces. Let's get rid of the green. So we know the centroid of here is right here, and right here. Where's the local centroid geometrically relative to 0, 0? Where is that local centroid of that piece located? Well, we know that, for one, it's going to be what? 4 over and 1 up, because we're going to the center of that rectangle. So it'd be 4 over and 1 up. What about 2? Well, we know we're 5 up here, right? So we're going to be 4 over, because 4 over once again, and up. 2 plus 5 makes 7 to get to that center of that individual piece. What about 3? Well, 3 we know is vertically up 1 inch here. So we're going to be up 2 to here, 5 to there. So 2 plus 5 is 7, 2 plus 10, we're 10 up here and 2 up here. So we're up 12 plus 1 is 13. So this is 4 and 13. Now what we want to do, we have the local centroids. But we need not to take an average of these, because we need to account for a weighted average, meaning that we got to account for the difference in area for each of those pieces. So I'm going to say xi times a, yi times a. So xi times a, 16 times 4 gives me what? 16 times 4 is 64. 1 times 16 is 16. 4 times 30 is 120. 30 times 7 is 210. 16 times 4 is 64. 16 times 13 is 208. Which now we have a weighted average. So I want to sum these up. So I sum up the XIAs, I get 248. I sum up the YAs, I get 434. Now we know that centroid, let's move this over a little. We know our global centroid, our global, not our individual local, but the global of the overall body. Our global centroid is going to equal summation of XA divided by AT, comma, summation of YA divided by AT. We take the weighted average of each of the centroids, divide by the total area. So in our case, we have 248 divided by 62, 434 divided by 62, and that produces 4, 7. Now, for this case, because it was symmetrical, we knew it was going to be right here. We knew it was going to be 4 over and 7 up. But mathematically, we've just shown how to obtain the centroid of an irregular shape by breaking it up into small components, analyzing each component, and adding them back together. Just like a complicated problem is just a series of simple problems that you solve, and then take all the solutions and add them together to answer the complicated problem. So now we have our global centroid. Come along with me. We'll put it back as 0, 0. So we got the centroid now. Now we want to find IX. We have a local component of our IX, which we know is BH cubed over 12 for a rectangle. So we know our local IX is going to be BH cubed over 12, meaning that the moment of resistance, the moment of inertia, or the bending resistance of this piece right here, we can calculate as a simple rectangle. And obviously, piece 2 should have a much higher resistance to moment, to bending, than piece 1 and 3. Let's go ahead and calculate those. So we get 5.3, 250, and 5.3. So that's our local. But moment of inertia has two things. There's two components to moment of inertia. One is its individual resistance. So the individual resistance of this to a load will contribute one piece. But the second part of this, the load is actually applied at the centroid. You can assume the load on a body is going to act at the centroid of the body in concept. And if the body resists, it's going to resist about the centroid of the body. The centroid of the body is offset from this individual piece. Our centroid was up here. And you can see this effect if you take this piece and do this, versus you stick this piece out here and you do this. Same exact member, right? Same exact member, but it's a lot harder to swing it when it's clear out here versus in here, right? I can swing it very quickly in here, but when I put it out here, it's a lot harder to swing. Why? There's a greater distance. Remember, we talked about a moment, right? We said a moment is equal to force times perpendicular distance at a point. So force is equal to, a moment is equal to force times its perpendicular distance. In a sense, moment of resistance is the same thing, or resistance to bending is the same thing. The greater the distance away that object is, the harder, the more resistance to bending it contributes, the higher its moment of inertia. And you can see that with this versus, real quickly in here, versus this. To calculate for this offset between the local I and the global I, right? This is my local Y, and this is my global Y. There's a distance there. There's an offset between the local Y and the global Y that's going to resist also this bending. And this contributes, this offset, Ix is equal to the area of the object times Y global minus Y local, this distance squared. So this distance right here between global Y and local Y squared times the area is going to contribute to a resistance to bending also, or contribute to your moment of inertia. So we have area times Y global minus Y local squared, because our loads are coming down this way. So the distance offset plays a role. When we calculate those, we get 64, oops, I'm sorry, my area for 1. So that's 16 times Y global, which was 7, minus Y local, which was 1, squared, which gives me 576, 2 area times Y global minus Y local squared. Bigger area, 30, times my global is 7, my local is 7, squared, 0. There's no contribution because the centroid of part 2 is at the center of the body. So there is no additional resistance by being offset. Then 3 is equal to 16 times 7 minus 13 squared, which is 576. You notice you didn't matter if you were down or up. The square accounted for that. Negative distance, positive distance, squaring it accounted for that. So we got 576, 0, 576. And you can see in this case, we got a lot more contribution to resistance from the two flat areas because we separated them out in a distance away from the center. Therefore, we got what? A total Ix of 13 inches to the fourth, or 1412.7. And hopefully now this somewhat explains this concept. If you look at it, this is an engineered wood die joist. We have material here laying flat. is separated out from a distance of the centroid. Because you can tell, while we had a bulky piece in here that gave us this, we got a lot more resistance to bending from here and here than we did from this center section. This contributed over 1,000, where this only provided 250, and in our problem, this was a bulky 250. Let's go through and do this in Excel. So, I'm going to have an ID, which are 1, 2, 3, right? A B, an H, which notice when I type in alpha values, they go to the left. Numeric values go to the right by default in Excel. And if I had an alphanumeric, right, it would be treated as an alpha, go to the left. That's how you can quickly tell if you have an alpha or a numeric, or an alphanumeric. Alpha and alphanumerics go to the left by default, numerics go to the right. So, we have 8 and 2, 3 and 10, 8 and 2. Area total. Plus this times that. And anytime I have an equation, I always come in, I change the color of the equation to blue. I don't like these blues. Here, I'll bold it. Let's get a different blue. Put that blue. That looks better. You can bold it and copy it down. And the reason I do that is black is just default values. They're givens. Blue is your calculations. So we have an area total. And then I have a local centroid, xi, yi, and that was hand put in at 4.1, 4.7, and 4.13. XIA, YIA, plus that times that, and plus that times that. Both equations, bold them, copy them down. We're going to do an at sum of those values, and this is my area total. Once again, that's the equation. Bold. Paste those over for my XA, YA, and my centroid. X, and my centroid Y. My centroid X is XA divided by AT, and YA divided by AT. Once again, we can bold these. Continuing on. Then I have IX local, which is base times height cubed divided by 12, and IX offset, which is equal to area times plus the area. Actually, this is just I plus the area times the distance of y global minus y local squared. Now, everything else I've been doing has been relative to that position. I global is actually a fixed cell. So when I copy this down, I want this to remain G3. I'm sorry, E10. So I'm going to come in here and put dollar signs here around E10. Both of these are bold. But if you look, this is C3, D3, right? E3, G3, and E10. When I copy these down, look what happens. I have C3, D3. When I copied it down, it went to C4, D4 because it was relative. It was a relative reference, a local reference, not a global reference. Look over here. E3, G3, when I came down, E4, G4, but this did not go to E10, 11. Notice it's E10 here. It stayed E10 here because we fixed it to that cell. So when you copy it relatively, it went straight back to that cell. So my IX total is going to be that sum so there's my IX total. Once again, we'll bold it and go like that. So we have our spreadsheet set up, which matches what we obtained by hand on our value. Well, let's say we take this same object right here, and I'm going to paste it. I'm going to rotate this 90 degrees. So it looks like that. Taking our same I section that we take, and now I'm just going to rotate it 90 degrees. Same exact material, same exact section, but now what is it? My centroid is now here at 0, 0. 1 has a centroid here, here, and here. So 1 is going to be a centroid of 1, 4. So this is 1. 2 is going to be at 7, 4. And 3 is going to be at 13, 4. Let's go back and change our values. So 1 has a base now of 2 and a height of 8. 2 has a base of 10 and a height of 3. 3 has a base of 2 and a height of 8. My x1 is going to be 1. My y is 4. This is 7, 4, 13, 4. What happened? Look at our centroid now. I mean our IX value total. We went from being upright when we were upright on this thing, right? We had 1413 units of resistance to bending. So when it was upright, like this, and this is a bulky section, it's not a flimsy little section like this. This was a bulky, thick middle member. We had 1413 units of resistance to bending. Yet when we rotated that on its side, we dropped clear down to 193. We went from 1413 to 193 just by rotating this around. And now you can see here we have a lot of resistance to bending, but when we rotate it around, now it's very flexible. These are the cross-sectional properties. This is what we're looking at. Moment of resistance, moment of inertia, or resistance to bending in terms of a concept. So this concludes our introduction to object section properties for today. Thank you.